Indices and logs. So in this section we're going to be looking at, well, what is a log and how can we go about using our log rules, which is in our maths tables on page 21. So this guy here pictured is John Napier, who was a Scottish mathematician, and he's famous for inventing logs. So he invented these logs for allowing for easier calculations of products and quotients of very, very large numbers. In the 2023 paper 1, question 3, we were asked to actually explain what a log was for the first time. So in general, we say a log is a mathematical operation that determines how many times a number, which we call the base, is multiplied by itself to reach another number. So this has many, many uses, such as the Richter scale for measuring earthquake magnitude, decibel scales, looking at sound, pH scales with acids and bases, and even trying to convert distances in stars into a graph that can be easily visualizing these large distances. If we look at page 21 in our maths tables, we're going to see that there's clearly a reverse representation between logs and indices, where we're going back and forth between the two. So we need to be able to write it in exponential form or write it in log form and convert back and forth. So we're going to have a look at how to do this in our first example. So if we're looking at the first one where it's an index form, we have a to the power of x equals y. So we refer to a as the base number, x is our power, and if I raise that number to a given power, we're multiplying by itself a repeated number of times, we're going to get some bigger number. When we're writing it in log form, we say it's log y to the base a equals x. So we always tend to say the base after y rather than log a y. So we can see there's clearly a direct link to the two. So the a in the index form is the base in the log form. X is the power in the index form, is going to be what the value of the log is equal to in the log form. And then the y is the number in it. So in other words, it's log of our number to a given base is equal to the power from the index form. So it's always better to write the letters a, x and y, whether we're in index form and changing to log form, or whether we're in log form and changing back to index form. And then it's much, much easier to use this equation on page 21 in our tables. Okay, so with our three examples, we're going to write 27 equals 3 cubed in log form, 5 cubed equals 125 in log form, and 2 to the minus 1 equals a half in log form. So I'm going to write the letter A. So we're going to write a to the power of x, so therefore that has to be our 3, and x is 3, and it equals a number which is y. So applying that to my log, it's going to be log y to the base a equals x, so therefore that's going to be log 27 to the base 3 equals 3. If I do the same for 5 cubed, well, a is 5, x is the power, and y is the number. So therefore that becomes log y to the base a equals the power. And if I do the same for the last one, we have 2 to the power of minus 1. So 2 is my base a, my power x is minus 1, and y is the number. So changing that to log form, it's log y, which is a half, to the base a, which is base 2, equals the power, which is minus 1. Now we can check these answers are correct on our calculator, so we're going to have a look at two different calculators to check these. So if we're looking at the Casio FX85 GTX, then we can see that there are 3 buttons for logs on this calculator. So the one that we're going to focus on for checking our work is this one here, and underneath the on button. So it's log box to the base box. So when we click on that button, the first cursor that's going to flash up is the base. So we'll put in base 5. Then inside the brackets, we'll put 125. And always make sure that those brackets are closed. And then when you press equals, we can see we get 3. So we know our answer is correct there. These other 2 log buttons are very important ones also. We have one which is just log. And when we press that button, log is basically log to the base 10. So when you have log to the base 10, we generally don't write base 10, we just write log. So if I had log 3, that would mean log 3 to the base 10. If I look at the button to the right of that, we have, it looks like the word in, but it's actually ln, and ln stands for natural log. And natural log is basically log to the base e, where e is known as Euler's number or Euler's number. And this is an irrational number, which is a bit like pi. We can abbreviate it to 2 decimal places, is 2.71828, and it keeps going. So if I'm rounding that to 2 decimal places, that would be 2.72. So because we have 3 buttons there, we have to always make sure that we're pressing the correct one. So if we have a base other than E or 10, then we will always use the one that has the boxes in it. Now we have the new version of the Casio calculator, so it means we have to actually search for our log buttons. So this is the Casio FX83GT-CW. Now we can clearly see the log to the boxes are there underneath the tools button. So if we press that, we can again just type in our base and our number. So we could type in log 125 to the base 5. And if we press our equals button, we'll get 3. But if we're looking for the other 2 log buttons, the log to the base 10 or the natural log, then we can click on the catalog button, which I've circled here, and up will come up function analysis. And then once we've clicked on function analysis, we can see we have 3 options for our logs. So we have our log to our base A, which is the normal button, or we have the second, which is the log, which is obviously our log to the base 10, and then we have our natural log option, which is log to the base E. And again, we can see that that is the shift button also down here. So 2 different ways of accessing those buttons. So if we want to go in reverse then and go from logs back to index form, again, if we label A, X, and Y, so our base is A, 16 is going to be Y, and that equals X. Then if I change that back to index form, it's A to the power of X equals my number. So in other words, 2 by 2 by 2 by 2, in other words, 2 to the power of 4 equals 16. Again, if we do the same for the next one, we write our base as A, 128 is going to be Y, 7 is going to be X. So in index form, then that's A to the power of X, so 2 to the power of 7, equals 128. If we're looking at the last one there, then again, our base is A is 10, Y is 1,000, and X is 3. So therefore, it's A to the power of X equals 1,000. So again, 10 cubed gives me 1,000. So all we've been doing in these examples is seeing, can we go back and forth from logs to indices? So of course, if we're looking at one where we're not actually given the answer, we then can see clearly how we can use this to solve. So for example, if we have log 3 to the base 9 equals x, or log 64 to the base 4 equals x, or log 1 over 81 to the base 3 equals x, and in each case we have to figure out what is our value for x. Well, obviously we can just plug that into the calculator and we'll get the answer. But if we go from log back to index form, so a, y, and x, well, that's 9 to the power of x equals 3. And now I can apply my indice rules where I want to make both sides the same base. So 3 squared is 9. So that basically means that 3 to the power of 2x must equal 3 to the power of 1. And I can say, well, the powers therefore have to be the same. And that means that 2x equals 1, and therefore x equals a half. So what that basically means is that if I put log 3 to the base 9 into my calculator, I should get a half for my answer. If I do the same for the next one then, again, base A is 4, y is going to be 64, and x is x. So if we change that from log back to index form, we have a to the power of x equals 64. Well, if I make both sides base 4, well, we have 4 to the power of 3 is 64. And then by equating the powers, so the left equals the right, then x must equal 3. So again, what that means is that log 64 to the base 4 has a value of 3. And if I do the last one here, again, base is a is 3, y is 1 over 81, x is x. And therefore, if I write that as a to the power of x equals 1 over 81, a little bit more work to be done with this one. So 1 over 81 can be written as 1 over 3 to the power of 4. And of course, from indices, we know that if we have 1 over a number, that can be written as 3 to the power of minus 4. And again, bases are the same left and right there, which means the powers have to be the same. So if I equate the powers, I get x equals minus 4. So again, what that means is that log of 1 over 81 to the base 3 has a value of minus 4. Okay, so for the second half of the video, we're going to look at the rules on page 21. And there, if we look in the middle, and also if we look at the right-hand side, we're going to see all of our log rules, whereas everything on the left-hand side here is our indice rules. So again, totally interlinked, being able to go from one to the other and apply all of these rules on page 21. If we know how to use them, well then the questions become very, very easy. So we're going to focus on the kind of main rules in this video, and then in a later video we're going to look at this bottom one here, which is called changing the base. So our first one is log xy to the base a equals log x to the base a plus log y to the base a. So first thing we see here is that the bases are the same for these rules. So we always check, are the bases the same? And if so, then we can use the rule. So this rule is basically used for when we're adding logs of the same base. And what we can see is when we add logs of the same base, then it's going to be the product of the two numbers. So if, for example, we're asked to simplify log 6 to the base 3 plus log 4 to the base 3, we can first see that they both have the same basis, the base 3, and therefore 6 is going to be the x in the equation and 4 is going to be the y in the equation, and 3 is obviously the a in the equation. So what that basically means then is if I have log 6 to the base 3 plus log 4 to the base 3, then I take 6 and I multiply it by 4, which gives me log 24 to the base 3. So in other words, log 6 to the base 3 plus log 4 to the base 3 has exactly the same value as just getting log 24 to the base 3. So the second rule is where we have log x over y to the base a equals log x to the base a minus log y to the base a. So again, this rule basically means that if the bases are the same and we're subtracting our logs, then we basically divide the first number by the second number. So if we have log 15 to the base 3 minus log 3 to the base 3, I check my bases are the same, so they're both base 3. And then I divide 15 by 3, and that's to the base 3. And therefore that simplifies to log 5 to the base 3. So the third rule down is where we have log x to the power of q to the base a. And in this case, if we have a log raised to a power, then we bring that power down in front of the log. So the q is then going to come down in front of the log. So for all these rules, we can go left to right or right to left with it. So say, for instance, if I have log x squared to the base 4, then that can be written as bring down the power in front of the log. So 2 log x to the base 4. Or I can go in reverse where I have a 3 in front of the log and I can raise that to the power. So then that could be written as log 2 to the power of 3 to the base 6. And obviously 2 cubed is 8. So 3 log 2 to the base 6 can also be written as log 8 to the base 6. This rule in particular comes in handy when we're drawing our graphs because it makes it a much neater, quicker way of filling out our tables. So the fourth one down is log 1 to the base a equals 0. So you can try this out on your calculator, but basically if we have log of 1 to the base 5, and we put that into our calculator, we're going to get 0. If I have log 1 to the base 10, I will get 0. If I have natural log of 1, so in other words, log of 1 to the base e, that is also 0. So basically this rule is telling us that log of 1 to any base is always going to be 0. So why is that? Well, if I remember going back to my index form, so my base is a, my number is y, and the power is x. So if I write that log rule as a to the power of 0 equals 1, and that's because anything to the power of 0 is always going to be 1. So therefore, if I go in reverse, well, log 1 to any base is always going to be 0. Okay, so if we're looking at the fifth one down, we have log 1 over x to the base a, and that equals minus log x to the base a. So let's look at this one a little bit closer. I have log of a number over a number, so in other words, I'm dividing. So if I go back to rule 2, that means that I can separate that out into log 1 to the base a minus log x to the base a. And now based on the previous rule that we just looked at, rule 4 there, log 1 to any base is 0. And therefore that leaves me with 0 minus log x to the base a, which is minus log x to the base a. So top right hand corner we have rule 6, which is where we have log a to the power of x to the base a is equal to x. So again, if I look at rule 3 tells me that if I have a log raised to a power, I can bring that power down in front of my log, which gives me x times log a to the base a. And then this log a to the base a is a very interesting one, because that basically means that log of any number to the same base is always going to be 1. So I could go to my calculator and I could type in log 10 and I'll get 1, because remember log is to the base 10. If I type in ln e, I'll also get 1, because remember ln is log to the base e. If I type in log of 23 to the base 23, I will also get 1. So as long as these two numbers here, the base and this number here, are the same, then we will always get 1 for our answer. So therefore this log a to the power of x to the base a becomes, bring down the power x times log a to the base a, which we now know is 1, and therefore my answer is always going to be x. So say for instance I have log 3 to the base 3 to the power of 4, well then that's going to be 4 times log 3 to the base 3, which is 4 times 1, which is 4. So once we get the hang of it, we can see that if I have, say, log 5 to the power of 7 to the base 5, then the answer is always going to be the power, as long as these two numbers are always the same. So if I have one more where I have ln e squared, well then that's going to be 2 times ln e, and ln e is always 1, so therefore that's going to be 2 times 1, which is 2. And again, we can see that that is the power. So 2 very important notes with our logs, and these are going to be very important when we're solving log equations. If I have log of 0 to any base, if you go to your calculator and you type in log 0 to the base 10, log 0 to the base e, log 0 to the base 5, log 0 to the base 100, then what you'll always get is math error. In other words, this is undefined. We cannot solve log of 0 to any base. And again, the reason for this is if we go back to indices, there's not going to be any power of x that gives me 0 as an answer. Because if I multiply a number by itself a repeated number of times, I can never, ever get 0. Okay, so our second important note then is if we take our calculator and we check log of any negative number to any base. So you could do log of minus 10 to the base 3, log of minus 2 to the base 5, log of minus 3, ln of minus 5, any of those numbers. And again, you'll see that you're going to get math error again, which means that we say that this is an undefined. We cannot solve these values. So again, if we're looking at indices, well, what does that mean? So if I can convert that back to an index number, there is no value of a raised to a power of x that can ever give me a negative number. So if you remember when we were drawing our exponential graphs, the graph was always above the x-axis. In other words, any input for x always gave me a positive output for y. So a good thing to also highlight is that our base number is always going to be a positive number too. So all of these cases here, log minus 3 to the base 4, log of minus 6, log of minus c, natural log of minus c, all of those would give me an undefined answer. So if we go to Active Maths Book 1, we look at page 187, and we have a look at question 1, part 1, part 4, part 6, question 2, part 4, part 5, part 6, question 3, part 3, part 4, part 5, part 6, part 8, question 4, part 5, part 6, and part 7, and question 8. And in each of those, you're just literally changing back and forth from logs to indices, or you're applying your log rules on page 21.